in the principle of the electric field is almost the same about the it's the same with the EFM in the morning. It just tells us the charge distribution on the surface, but in the physical principles we use it a little bit different. So let's start. I am not I don't like the way I show in the slides today, but I just follow the tradition. So so we will use that. So the traditional KPFM, we're always starting from the Fermi energy and the Fermi level. It gives us a story, something like that. So the so-called Fermi level or the work function, it gives us an idea like this. So we all know in the solid, all the electrons is confined by the nucleus. So we will define the energy level of the electrons inside the solid, and it will form this kind of the energy bond, the blah 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 stuff. And but in principle, all these electrons, they are confined by the nucleus. So the energy of the electrons inside the solid, it should be negative, right? The same as the hydrogen atoms. And then we define the energy level of vacuum as the zero. That's a basic principle. And then we call at 0K, the highest level of the electrons occupied by electrons. We call this level as the Fermi level. Okay, that's the Fermi level. Of course, when the temperature increases, the Fermi level will, the electrons will go to the upper energy levels. It's just the Fermi-Dirac distribution or the Boltzmann distribution, something like that. Okay, so that's the Fermi level, and then we define the energy difference between the vacuum and the Fermi level as work function. So the work function is just equals to the 0 minus Fermi level, right? Just equals to that. And in the textbooks, the unit of Fermi level and the work function, they use the E volts, the electron volts as it's the unit. It just means the energy to move one electrons from the Fermi level to the zero. It equals to that. Of course, it equals to the 1.6 times 10 negative 90, right? Something like that. That's the Coulomb times volts. Then it's joule, right? That's the unit transfer. But we would use the E electron volts, which will be more easily for us to use. That's the basic idea of the work function. Okay, and then in the I remember it's in the 19th century, the famous Kelvin guy, the Sir Kelvin, he found one interesting thing, and he found if I have two material, if I connect two metals together, he found there is a potential difference, or they found there will be a charge could be transferred between these two metals. For example, we place an aluminum here and a gold here. Okay. Today we already know the aluminum is more active than the, I'm sorry, it's the same, to be more active than gold, which means the Fermi level in aluminum is higher than the Oh, it's okay. It's higher than the Fermi level of the gold. That means this electron is more active. It can be popped out, right? So once we connected these two metals, and the Sir Kelvin found there is a potential difference. But of course, today we will know this is due to the difference of the Fermi level or the work function. Okay, once we connected these two metals, the electrons will go from the higher Fermi level to the lower Fermi level. And as such, it will establish, it will make this aluminum to be positive charges and the gold to be negative charges. And then it will generate an electric field, right? This electric field will prevent the electrons continuously transfer from aluminum to gold, right? So it will be this kind of electric field. Okay, this electric field will just prevent the electrons goes on. And when it goes to the balanced, we would know the Fermi level on these two will be the same. And then the electrons will not continuously move on, but then it will establish the Fermi level will be the same. So the electrons will not continuously goes on, but as a result, we actually establish an electric field. And for the electric field, we know another way to describe the electric field by define as the gradient of potential, right? And of course, we know here the aluminum is positive and the gold is negative. We would know the potential difference. This is lambda, so I would use the potential difference between aluminum to gold should be equals to the Fermi level difference divided by charge of 1 electrons, right? This potential will prevent 1 electrons from here to here. That's our established, that's our mathematical relationships. So he established this kind of so-called contact potential difference. And in quantity, it equals to that. So if we can measure the potential difference, we can measure the Fermi level difference. We measure the Fermi level difference, we measure the work function difference. So this Kelvin's method is used to measure that. So how to measure that? So the Sir Kelvin found a way to measure the potential difference between these two metals. So he established this way. If I have I already have the aluminum to be positive and the gold to be negative. So how I can know the potential difference between aluminum and gold? So Kelvin established a loop here. So he put a positive charge. So he put a power source here. And then I put an ampermeter here. Okay, and then he would continuously adjust the power source and to observe the ampermeter. Once the ampermeter equals to 0, then the power source, the direct current, the DC voltage on this power source will equals to the potential difference. Right? That's the whole idea of this kind of experiments. And I'm sure you also did some experiments when you in the first year of your university. I gave you a battery, and this battery, how you can measure the voltage difference between the positive pole and the negative pole. So in the university's experiments, we would give you a power supply and give you ampere meter. How you do that? You put a switch here, and then, for example, I know this one is around 1 volt. I know it's around 1 volts. How will I do? I will put this one 1 volts, and then I turn on the switch, and I would get some current showing this ampere meter, right? So if the ampere meter is go through this way, I know, okay, this side is higher. I need to reduce that one. Then I shut down the switch, adjust the voltage again, and turn on, right? Because we cannot keep this always on. If I turn this switch always on, the charge will go through this batteries this way, and the voltage on this battery will reduce. So the voltage on this battery will always change. So we have to do this one back and forth to change the switch back and forth. It's the same here. If for example, if I already have this one is the positive, this one is the negative, and then I turn this switch on. This one is positive, this one is negative, so this one potential is higher, so the electrons will go through this way. And then once the electron goes to that way, the ampere meter will read its current, goes from higher to 0 quite quickly in the experiment setup. So finally, if we do it in this way, we are actually change the voltage between these two. So we have to use Kelvin's method. We need to add a power source here by adjusting this power source to capture when the ampere meter gives us 0 current. That's the whole idea of the Kelvin method. It's kind of a balanced method or a static method way to do that, because we don't want any current to go inside the loop. So this method was invented, and then some guys came up with an idea how I can adjust this method to be the measurement to be more stable. So he found a way. The idea of Kelvin is you want the current to be 0, and then the VDC equals to CPD. But I don't want the loop to be continuously on. I need to turn on the switch on off frequently, and I still have a defect that there will be some current goes inside the loop. So these guys invented this way. I still have a gold. I'm sorry, I still have aluminum. I still have a gold. And this one is positive charge. This one is negative charge. I want to measure the potential difference between these two. So I put them inside a loop. Same as Kelvin. The whole idea is, again, the VDC here should equals to CPD, then this ampere meter will be 0. But he made some changes. He made a motor here. He made the motor connected to, say, gold atoms, gold plates. And then he made this motor to move back and forth. So when this motor is moved, the distance between the aluminum and the gold, it will change periodically. So I will define this D between aluminum and gold equals to a constant plus how it moves. if we define the moves as a sinusoidal move, delta D plus sine omega t. Okay, and so this motor will move. Then we know these two plates actually they form a capacitor. So the capacitor equals to A epsilon over D, right? So it gives us the A epsilon divided by D0 plus delta D sine omega t. Okay, what's current? Current is actually the derivative of capacitor over time. So this one is just epsilon A delta D now omega cosine omega t plus D0 delta D sine omega t squared. Okay, something like that. Doesn't matter. Something like that. Something like that. So we get this thing. So we can tell the I is always not zero, right? The current is not always zero. So once our motor is moving, there will always be a current here. And then only if what? Only if VDC equals to CPD, the current is constantly zero because the potential of these two boards, they are same potential. So no matter how you move this motor, no matter how you change the capacitor, the voltage between these two boards is the same. The electrons cannot move, right? That's the whole idea of this guy's modification. I forgot his name. It's from Norway or somewhere. I forgot. It's somebody. Okay, so that's his modification of Sir Kelvin's method. So with this setup, the experiments will be much easier to do. So he just turn on the switch, adjust the, once he turn on the switch, there will be always a non-zero current. And then he adjusts the VDC. Once VDC equals to the CPD, the current is zero. That's his modification, and it's a quite smart way. So, so Sir Kelvin and this gentleman invented this method to detect the potential difference, and then they get this method done. So we want to use this kind of method to measure the surface potential. Okay, how AFM can do it? So the AFM should be quite simple. It's the same. This is the probe. This is my surface. Again, I lift the probe. I lifted the probe, so it will form a what? A capacitor, right? It forms a capacitor. So the easiest way I would do is I make the same as Sir Kelvin's setup, and then I add a VDC here. Okay, I add a VDC here. I am here to get an amperemeter. I'm looking at this I'm looking at this the current. Okay, I want to do the modification of these guys. Okay, I net the probe to do what? Tapping. That's it, right? That's the quite simple, totally the same as this Sir Kelvin's method. But once we came back here, we found, the AFM is not that good at measuring current. The AFM is invented to measure the force, those stuff. He is not good at this current. So the Kelvin probe, the force microscope, he made some changes. he did not put an ampermeter here. But again, he should find a way to replace the ampermeter. So he think about this in this way. The total idea of Kelvin's method is if the potential of the probe equals to the potential of the sample, then there is no current. But again, we think about in this probe, if our probe, say if it's a metal, once we place a metal inside an electric field, there should be an electric field force. We have the EFM in the morning. So we have the electric field force. But if the potential of the probe and the sample, they are the same, that means they are same potential. There should be no electric field force. So we get the same idea in the morning. We don't measure anything about current. We just measure the electric field force sensed by the probe. And we adjusting the VDC. Once this force is zero, this VDC is equals to the potential difference, right? That's the idea of our Kelvin, the KPFM. Okay, so quite simple. So then we just go through the details about how we get this done. Okay, so at beginning, we do it the same as Sir Kelvin. Sir Kelvin, this is the probe, this is my sample. And then I just need to detect the force on the probe. So the force is what? Is the electric field force. So I write an electric field. So I give it a load as Fe, okay? Electric field force, something like that. So once the potential, I would say, then I can adjust the tip bias. I can adjust the tip bias. So I change the tip bias. I change the tip bias only if the tip bias equals to the contact potential difference between tip and the sample. The Fe is zero. So the only question is how we measure the Fe. So to measure Fe, easy. I want to measure the electric field force, so I lift the probe. So I will use the lift scanning. Second, how we can measure a force? Quite easy. There is still a laser, there is a detector. So once there is an Fe, this Fe could be positive, I'm sorry, could be repulsion, could be attraction. We apply a force on the tip, so the deflection will equals to the Fe divided by K. And the deflection is equal, is what? It's proportional to vertical change. So what I have to do is to check vertical value. If this vertical value equals to zero, then my tip bias equals to the CPD, right? But you have done the AFM many times, you will know this vertical value is easy to change. Once you engage, the hydrodynamic force will cause the vertical change. So this one is too sensitive. It can be affected by the vibration from the environment. It can be affected by your sound even. So this one is too sensitive. If we directly look at its vertical value, it's hard for us to detect if it's zero or not. So how we do that? So due to the time limit, we only have the 3 days for the training, because on my plan originally I would discuss one technique called locking amplifier on the first day. So today I just gave a brief introduction about the locking amplifiers, the technique, just quite shortly. So we think about a story. We think about scenario like this. You all know telephone. You all know telephone. What's the basic principle of the telephone? The telephone is just a method to let the people far away from you, they can hear your sound. That's the total idea of the telephone. So for example, I am here. That's me. Okay, I stand here, I make some sound. What's the sound? It's just the vibration of the air. It's just a vibration of the media. And this sound can be easily absorbed, can be easily reflected by anything between me and the receiver, right? Because this sound is the wavelength or the frequency of this sound is too low. It can be easily absorbed. So how we do that? If we make our sound, we combine our sound wave times a high frequency wave. For example, I combined with, I don't know what's the frequency of this one. It's something about gigahertz. So I times it a gigahertz wave. So my sound wave is something like this. It's not a sound. It's not my sound anymore. It's a sound times on a gigahertz waves. We call this step what? Modulation. But now my sounds, the frequency of my sounds now is gigahertz. Its frequency is no away from the no away from the resonance frequency of my buildings, of the desk, or anything. So at this time, the sound wave cannot be easily absorbed by the buildings, by the hills, by the bridges, blah blah stuff. And then this wave can transfer a long distance to the receivers. On the receivers, what they get? They get the sound wave times sine gigahertz t, right? So, but he cannot understand this wave, right? Because this is gigahertz waves. So what he need to do? He need to demodulate here to get rid of this gigahertz, and then came back to him is the sound wave. Okay, so that's what your telephone did. Inside the telephone, you pay some money to a guy's named the telecom company. I don't know what's the company in China, in Hong Kong, but those are just the big money guys. So what they have, they just define this frequency. He buy this frequency, only he can use this frequency. And then you buy him, and when you talk to the phone, he will modulate your sound with this gigahertz, and then goes a long way to your receiver. And your receiver pick it up, demodulate this kind of gigahertz, and give you the sound. That's the idea of the telephone. That's the idea of telephone. So it's the modulation and the demodulation. And these ideas why it could work? Because the gigahertz is larger than the resonance frequency of the buildings. And from the beginning, you can already know the resonance frequency is proportional to K over M. So those buildings, those hills, the M is so large, so the resonance frequency is quite low. So if we use this way, we can avoid its resonance. So that's how this telephone can work. So came back to us. We want to detect the electric field force. And we found in our AFM way, the best way to measure it is just to measure the vertical. But the vertical is too sensitive. It can be affected by sound. It can be affected by vibration. It can be affected by hydrodynamic force. It's too sensitive. Same as your sound wave. So how you do it? You modulate it to high frequency and then demodulate it back. We can get easily to get this vertical. That's our ideas. Okay, so let's just show how the telephone works in the KPFM. Okay, so the idea is we want this vertical to be something like sine omega t, and this omega should be large. And we know the buildings, the hill, the buildings, the sound, the frequencies. So we choose this omega should be kilohertz level. That's the idea. We want this to be kilohertz level. So how we achieve this modulation? Okay, so that's the idea of the KPFM. So we think about it in this way. We have a tip. Well, I'm sorry, we have a probe, we have a surface. There is a contact potential difference between the probe and the surface. Okay, I apply a tip bias here, which is VDC. And now I want my vertical to be modulated. How I can do that? Easy. I make the tip to be vibrate. And the vibrate, I made my tip to vibrate at a kilohertz level. And then I achieve the vibration. But this time, how I achieve this vibrate? Because I want my vertical to be electric field force. So I want this vibration also caused by the electric field. So we apply AC voltage on my tip. That means we apply an AC field between the tip and the sample. And then this AC field will drive the probe to be vibrate. And if our AC field is at kilohertz, the probe should vibrate at kilohertz, right? That's the whole idea, how we achieve that. Then let's do some mathematical calculation here. So let's take a look at the tip. So the tip is placed between the tip and the sample. So the tip let's take a look at its voltage or potential. It's the same. It will definitely affected by the contact potential difference between the sample and the tip. I apply a VDC on the tip. And ideally, this one should be the equal to this one. So this one will be canceled. That's our ideal, right? And then I apply VAC sine omega t. And I make this omega at kilohertz level. Okay, so the potential or the voltage on the tip is something like that. Then I take a look at this field, at this case. What's the electric field sensed by the tip? Okay, so how we do that? Of course, we can still use from the beginning, we can use the Coulomb's law, 4 pi epsilon 1, Q tip, Q sample, and this is Z lift square. But how to calculate Q tip, how to calculate Q sample, it's too difficult for me. So I make this model a little bit easy. This is tip, this is the sample. It just looks like a what? A capacitor. And the capacitor, the capacitor is just equals to the epsilon A over D. The D here is the distance between the tip and the sample, which is the lift height. It forms a capacitor, and the potential energy of this capacitor can be easily calculated as the negative voltage square. And this is a conservative, I'm sorry, this is a conservative field. So the field force can be written down as a negative gradient of my energy. Okay, and then it equals to the dc over dz times voltage square. Then I write it down. So that's the idea of this page. Okay, then that's high school. Then that's high school. I put this one here in. So it's dc over dz times cpd plus vdc plus vac sine omega t square. Okay? Just put it here. So we just put it here. Okay? So this one will be much easier. So we write it down. We just use the high school mathematics to get it down. So we will get 3 terms. One term, I think there is a negative here. The one term here is the negative dc over dz, and this one is the cpd plus vdc square. Okay, the second term is this one times this one, so it's the negative times 2 times dc over dz, cpd plus vdc vac sine omega t. Okay, and the third one is this one, so it will be negative dc over dz vac square sine omega t square. Okay, sine omega t square we just do some mathematics. Sine omega t, cosine 2 omega t equals to 1 minus 2 sine square omega t, right? So we just use this equation to get it back. So finally, it will be the same as that one. Cosine 2 omega t, and make this positive, add this 1/4. And at this term, we plus VAC square. Okay, that's it. That's our term. Okay, let's take a look at the three terms. The first term is a DC term, right? It has nothing to do with time. The second term is sine omega t term. The third term is sine 2 omega t term. What's our goal? We apply this AC field. We want our vertical to at omega level, to at kilohertz level. And what we get? We get this term. And if we take a look at this term, we will find the amplitude of this term is proportional to CPD plus VDC. That means if the amplitude of this term equals to 0, the CPD equals to VDC. So that's the idea of the Kelvin. So at this time, I don't need to take a look at the vertical, but I take a look at the vertical at omega. So I would take a look at this term. I would only take a look at this term. And at this term, I get the amplitude of my vertical. And the amplitude of my vertical will be equals to this one. And I only need this amplitude to be 0. I can get the CPD from the VDC. So this one, how we achieve that? We modulate the vertical value to make it vibrate at a kilohertz level. We finally check the amplitude of the vertical value. We get the signal we want. So this method, we call it amplitude modulation. Okay, so that's the back, the mathematical stuff of the KPFM. Okay, so we get back, make a review. So the idea here is we want to get the potential difference between the tip and the sample. We apply voltage on the tip. If the voltage of the tip is the same as the potential difference, then the tip will not sense any electric field force. But if we do it directly, we will find that this electric field force is too sensitive. So we modulate this force at a kilohertz level, and then we study the vertical value at a kilohertz level. And if the VDC equals to the CPD, the amplitude will be 0. That's the idea. Okay, so the basic is the same as the Kelvin's method. We want this two plate to be same potential. Then there will be no force. It's just another way to detect the force. Okay, so our way to detect the force is the telephone principle. We modulate our signal. Okay, that's the idea here. That's the idea here. Okay, so once you do the experiments, you apply a AC voltage. You apply a AC voltage on the tip, and then the tip will sense an AC field. and we detect the amplitude of the vertical value at omega. And then we adjust the VDC on the T-valves. Once the VDC equals to the CPD, the amplitude will be 0. That's the idea. Okay? It's a little bit long, but not that hard. Okay, so then our experiment will be the same as the EFM way. Okay, okay. So let's go through some details. Here is the details about the so-called locking amplifiers. It's just a way to tell us how we can get the amplitude out. It's just the technical things. So if you are interested in the how the locking amplifiers works, we can discuss later or in the hands-on session. So the next, let's go through some detailed stuff. First, I think this is the most important thing. First, the potential we measured here does not need to be contact potential difference. Okay, so the so-called Kelvin potential method, Kelvin probe, is coming from the contact potential difference, because that's the way how Sir Kelvin found it. So our textbook always use this way, but I don't want you to be confined by this concept. The potential can be any arranged. It does not need to be contact potential. For example, again, we go back to the sweater in the winter. You have a sweater. The potential on your sweater could be kilovolts or 10 kilovolts. It can be very high voltage. This kind of voltage is from what? It's from charging on the surface. It's not from Fermi level. And we can still measure this potential. Of course, this potential is no longer Fermi level. So the Kelvin potential method can measure any potential. It does not need to come from the contact potential difference. Okay, so if your sample is conductor, or sometimes semiconductor is okay, and then there is no external field, the potential we get from KPFM equals to the contact potential difference. It's from Fermi level or work function. Okay, only this case. If your sample is insulator or some stuff, no, the potential is from charge. Okay, so the potential is from charge. I understand in current study, the people choose the Kelvin potential method because they want to study the Fermi level or the work function. But we need to know the origin of this potential. We need to know the origin of this potential. If your sample is insulator, you do a KPFM measurement, you found the surface potential difference is what? 8 volts. There's no such materials, right? There's no materials. It has the Fermi level of 8 volts. No, there's no such thing. No, right? Because the insulator, the potential is from charge. Okay, So that's the most important thing. We need to know the potential can be anything. The potential can be anything. If you want your potential to be Fermi level related, you must need your sample to be conductor. Okay, because only in the conductor the electrons can transfer from your sample to the tip and cause the contact potential difference. Okay, so that's the most important thing. Second, so in our explain, we apply the voltage on tip, but of course the voltage can be applied on sample. So the voltage, we can apply the voltage on tip, we can apply the voltage on the sample. Anything is okay, anything can work. So but we need to discuss a little bit more here. So the idea, here is my tip, here is my sample. There is a potential difference between the tip and the sample. I apply a VDC on my tip. And what that means, if this VDC is our final results, if I apply VDC, I get the amplitude of the vertical to be 0. And then that means the VDC equals to the phi sample minus phi tip, right? My VDC plus the potential of the tip make it the same as the phi sample, make it the same as the potential of the sample. That's the compensation meaning. That's the compensation meaning. Of course, if you apply the potential, I use the blue pen. If I apply the potential on the sample, that means the potential VDC equals to the phi tip minus phi sample. Okay, that's the compensation means. Okay, so our results is always this VDC. Okay, so that's the direction. So if you apply your voltage on tip, the VDC you get is the potential of sample minus tip. If you apply your VDC on sample, the VDC you get is potential of tip minus sample. So you compensate on which one will be minus. Okay, that's the way. Okay, so if the potential is related to the Fermi level and the work function, what we can get from here. And then if we apply the voltage on the tip, the VDC will equals to the phi sample minus phi tip. Of course, it will be equals to the Fermi level of sample minus Fermi level of tip, right? The higher Fermi level will make the surface potential higher, right? Remember the idea of the aluminum and gold. The Fermi level of aluminum is higher than gold, so the electrons will go from aluminum to gold and make the aluminum positive and the gold negative. So the aluminum will be higher potential. So this one will be like this. But once it goes to the work function, it will be what? It will be work function of tip minus work function of sample. Because the definition of work function and the Fermi level, they are opposite, right? That's our idea here. Of course, if we apply the voltage on the sample, it will equals to the Fermi level of tip minus Fermi level of sample. It will equals to the work function of the sample minus work function of the tip. Okay, that's the difference between you apply on the tip or on the sample. But again, this one only works if your sample is conductive. If your sample is not conductive, you cannot even apply voltage on it, right? So and of course your sample is conductive, we can know, okay, this potential difference is related to Fermi level and the work function. Okay, that's the idea here. Okay, so just a brief just a brief introduction here is there is another potential in the in our material study, which is electrode potential. That's the electrode potential. It's just related to the electrochemistry. And the electrochemistry, we usually define it in the reduction. For example, we define this reduction of lithium ions get 1 electrons to be lithium. That's a famous one because that's our lithium ion batteries. Of course, we define this one's electrode potential. We know this value is about negative 4.7, something like that, volts, something like that. And this value is lower, means this metal is more active. And so there are some researchers from from our batteries or corrosions. They all know this kind of electrode potential. But the electrode potential is not the same as our contact potential here. So from the electrode potential, we will definitely know the phi aluminum is smaller than the phi gold. That's the electrode potential. But in our description about the surface potential, we can tell the aluminum surface potential is higher than the gold, because these two are different potential description, right? This potential is from the electrochemistry reactions, and this one is from the solid mathematics. I'm sorry, it's from the solid physics. They are different way. So we don't want it to be mingled together. Of course, it tells us the same thing. If one material or one metal is more active, the surface potential will be higher and the electrode potential will be lower, right? But they are not the same. So sometimes you will say some researchers, they found, okay, my metal is more active, its potential should be lower, should be more active, but no, not in our case. Okay, not in this surface potential. He's talking about electrode potential. Okay, that's the point 2 here. Okay, so then we came back again about our sample. So same as our EFM in the morning, our sample does not need to be conductive, right? Because our potential is not from contact potential. So our sample does not need to be conductive at all. Only if you want your sample, you want your potential value to be Fermi level related, the sample is conductive. Okay, I think I should write it down. The sample is conductive only if your potential is Fermi level related. If not, anything can be measured. You can even measure your sweater. Okay, so the sample does not need to be conductive. Okay, so that's the third one. Okay, the fourth one I think is related to our KPFM. So the fourth one I write it in the top. So the fourth one. What about the omega? Do we have a confine of the omega? We said the omega just need to be kilohertz to avoid those noise, but it can be anything or it has to be a certain value. Can we use 10 kilohertz, 100 kilohertz, or 101 kilohertz? Do we have a defined value for the omega? Any idea about the omega? Do we need any preference about the omega? If I choose the 10 kilohertz here, and then I change my frequency to 100 kilohertz, should I get the same potential value or not? Here, we only need the amplitude to be 0. Is there any frequency here in the amplitude? No, we don't define our frequency. Our frequency can be anything. Our frequency can be anything. So these frequencies, we can choose any frequencies you want. But again, if this frequency equals to omega 0, then the amplitude will be amplified by few times. And then the amplitude value will be larger, and it will make our measurement easily. So that's the idea here. Why your KPFM default setup, they always use omega 0. That's the reason. It can be anything. You reduce or increase the omega, you always get the same potential value. But we want our measurement to be more sensitive or more accurate. We make this omega equals to the resonance frequency of the cantilever, and then the amplitude is larger. That's it. So that's the whole idea of our KPFM. Okay, so the fifth thing is kind of stupid. It's come back to the technical again. So my amplitude, my field, my electric field force is dc over dz times cpd plus vdc times vac sine omega t. And I make it easy. Omega equals to omega 0. Okay, I get this one. And then I get the amplitude of this force. The amplitude of this force will be what? Will be dc over dz times cpd plus vdc times VAC. But again, the amplitude in our mathematical definition, it should be always positive. So the real amplitude of this one, we should add an absolute value of the term. Okay, so in our idea, the electric field force is proportional to VDC. That means the force and VDC should be something like this. And we want to get which points? We want to get these points. At this value, the electric field force equals to 0. That's the KPFM. We want to find this point. But once we take a look at the amplitude, it makes these things complicated. It makes us the amplitude over VDC, it comes something like this one, right? It will make something like this, something like this. Of course, we want to find these points. We want to find these points. Okay, to find these points, if you guys are designed KPFM, your idea is find VDC when amplitude is 0. How you will find it? You will adjust the VDC and then you want to find the lowest value. That's it. That's quite easy, right? But okay, that's the engineers from Brooker. They don't have enough pay, so they want to make these things quite easy. Okay, so how he can invent this thing? He came back to this function. He found that this function is quite easy because this is a linearship relation. This is a linearized relationship. So he wants his mathematics to be something like that. So he wants to be his design to be something like this. I adjust the VDC. I take a look at some value. If this value is 0, my VDC is correct. And I want this value to be proportional to VDC. That means if VDC increase, this value will increase. And it goes back to the linear relationship. He can design this algorithm quite easily. And he wants to use this algorithm. But he finally found, okay, come on. I'm taking a look at something like this. I don't want to design an algorithm to find the lowest point. He still wants to use this algorithm. So his idea is try to make this curve back here. So what he did, he make the things complicated, a little bit complicated here. He found, okay, so my amplitude is something like that. What about my phase? What about my phase? My phase is quite simple here because the phase only have 2 values. One phase value is 0. Another phase value is pi, right? Because the force is something like the force is something like this. So once the amplitude changes direction, you apply a what? Elective charge here. You apply elective here. Negative sine, cosine 0 equals to 1. Cosine pi equals to -1. So in his idea, it's quite simple. I just need to apply the phase value here to make this one back to here. So he make his calculations. He make his calculations something like that. So he has an amplitude. If I apply the amplitudes by the cosine phi, I change these terms to here. And then it's the same as the field, as the electric field force. And then he came back again. The VDC, the amplitude times cosine phi is proportional to VDC. The VDC increase, this value increase, and he easily find this value equals to 0. That's the Brook guys came up with this idea. Of course, it's not smart as us, okay? If we define our algorithm to find the lowest point, we don't need this kind of phase stuff. Okay, so he find this phase stuff, so it's only the if we have if we get this. So in the real KPFM in the real KPFM stuff, you will notice there is a so-called phase value, the so-called locking phase. Its use is to adjust this one. Okay, so if we are playing with the phase, we may have some messed up here. If our phase is not correct, for example, if our phase is messed up by myself, in the wrong phase, I make this one pi, this one 2 pi. Then it will give us, it will messed up because cosine 2 pi is 1 again. So in this kind of setup, the curves will be, I'm sorry, I use the black. It will be something like this. So at this time, the amplitude times cosine phi is proportional to negative VDC. The VDC increase, this value will decrease. But again, our engineer just use one algorithm. He only accepted these relationships. He does not accept these relationships. So if you found your curves goes to these terms, it will give you the bad results because he adjusted the voltage VDC to wrong direction. So it will reach VDC limit, which is positive negative 10 volts. So if you found your result is consistently positive or negative 10 volts, you messed up with the phase terms. Okay, but it's easily. Our software, and let me show. The software, okay, never mind. I can show you in the hands-on session. There is automatically phase setup values, but you just need to know how it happens. Okay, so that's just the Brooker's method. In the KPFM, you can use the KPFM from Brooker or from other AFM companies. The basic concept is the same. We just need to find this value. We just need to find this value. The only Brooker use this kind of phase stuff. The other companies, they use different stuffs. So, but the idea is the same. It's so we don't need to confine ourselves by those technical stuffs. So if, maybe in the future, you guys design the algorithm for the KPFM, you can use this way. Okay, find the lowest points. That's easily. That's easily. Okay, so that's the KPFM concept. Okay, let's just take 5 minutes break and then we can finish the lecture stuff. Okay, let's continue. So we just described something about the KPFM. So there is just electric. So there's a potential difference. So there's a potential difference between the tip and the sample. and we use the Kelvin's method to apply VDC to get this contact potential difference out, and to make this to make our measurement to be more accurate, we apply a VAC on the tip, and we want this measurement to be more sensitive. We make this omega equals to omega 0, and our signal is from the force, and then the force will be applied on the tip, cause the deflection of the force. So we just check the deflection using the vertical. And our signal is on the, I'm sorry, our signal is on the amplitude. So we call this method amplitude modulation. Okay, we call this method amplitude modulation. So our amplitude is just related to the force. But as we show in this slide here, the whole probe is conductive. The whole probe forms the capacitor between the force, between the probe and the sample. So the whole probe can feel the electric field force from the sample. So not only from the tip, from the whole probe, the cantilever, the shape of the other side of the tip can also sense the force from the surface. So this force or our deflection, it contains the end of the tip, the other side of the tip, and the cantilever. And the end of our tip is the most sharp. So only this part is high resolution. But the other parts, they are micrometer scale. They are quite large. So this one, those two things, is just a low resolution. But again, AFM probe is blind. He just sense it just sense the force. It does not know the force is from the end of the tip or other side. So if we just use the amplitude modulation, it actually no resolution. It just gave us no resolution. Okay, so it just messed up our resolution. So how can we increase the resolution? It's just a topic about how we can make the effect just focus on end of the tip. So the point here is we want to make our measurement to be local on the end of the tip. So how can we do that? So this electric field force we have discussed in the morning, that is related to the Z lift square, right? Because it's the Coulomb's rule, 4 pi epsilon 0 q tip q sample, right? That's just the proportional to the square. So if we want to increase its resolution, or we want our tip to be localized on the end of the tip, we want this force, we want this term to be more localized. So we want this term to be more short range. So if we take a derivative, this derivative will be just latitude 2 pi epsilon 0, and the Z lift third, and Q tip Q sample. So this one is third term. This one is square. So if we draw this curve, we will find this is distance. This is Z lift. So the force is something like this. That's the force. But for its derivative, it will be something like this. Right? Because it takes another derivative, it's third term, and this one is it's the square term. So this one is reduced much faster. I'm sorry, yes, reduced much faster than the force. So this one will be more sensitive. So this one will be more local. So the point is, if we don't detect the force, but to detect the force gradient, then this detection will be more sensitive. It will be more higher, the resolution will be higher. So the idea is here. So we adjust the VDC, and once this force gradient is 0, then we get it done. So how we detect the force gradient? We detect the force easily. We just detect the amplitude. But how to detect the force gradient? We have the morning session. We have the EFM. So our delta omega 0 equals to the negative 2 k omega 0 dfts over dz, right? If we can detect the resonance frequency shift, we can detect the force gradient. So the idea here is we want to detect the force gradient. We just detect the resonance frequency shift. So the idea is change to something like this. We have a probe, and this probe is under a contact potential difference. We apply a VDC on this probe, okay? And we want to measure the gradient, so we need to get the resonance frequency shift. So the point here is we want this probe to vibrate and then to observe its resonance frequency shift. So what we do in the morning, we make the probe to do the tapping mode, right? We make the probe to vibrate. So we apply a force F0 cosine omega 0 t. And then the probe is doing the tapping mode. And then we apply VAC sine omega t. And this sine omega t, this electric field force will what? Will change the resonance frequency of the tip. And then we detect the resonance frequency shift, then we can know this one. Okay, so the idea here is our VAC or our electric field is used to modulate frequency. After we modulate the frequency, we detect the frequency shift. We know the force gradient, and the force gradient will be more localized on the end of the tip. So we increase the resolution. So that's the idea of the KPFM, to increase the resolution. So we call this kind of method, we call this kind of detection method the frequency modulation KPFM. And in our software, we call it FM KPFM. So the FM KPFM is to use the frequency to frequency shift detect the force gradient, and the force gradient means higher resolution. And the first session we have is the amplitude modulation. Amplitude modulation is used to detect the force, and the force may have lower resolution. So that's the difference between the AM and FM. Okay, so in the icon in our MCPFM, we have both. You can just choose the one you like to do the KPFM. The most popular one or the most common one is the AM, is the amplitude modulation one, and you have many papers to describe this this method, and of course, you can use the FM if you need higher resolution. So this two method, it has some property difference. So the FM wave, it's high resolution. And because it only detects the potential from the end of the tip, so it's high accuracy. And of course, for the but it also has a disadvantage because it's detecting the frequency shift, it's detecting the force gradient. The signal is low. The signal is weak. Or in another word, the noise is large. So you may find the FM results is not that smooth, it's kind of noisy. But for the AM, it's relatively easy. So the AM, the property of AM is resolution kind of low and accuracy is kind of low, but it's really strong signal. It's strong signal, and you can get the result quite strong. Okay, so that's the two properties. That's the two properties. Okay, so in the KPFM, in our session, you can in the hands-on session, you can try both, and you can just feel which one is more preferable for you. And the parameter, the last parameter we would discuss here is the lift height. So we don't talk about the lift height here, but once we goes back, we can consider this thing. So the lift height. So how would the lift height affect our final results? How would the lift height affect the final results? So I think we have some physical questions, and these physical questions can be used for the high school Olympic the problems. So something like this. If you have a gold, if you have aluminum, if you have a gold, and then you use a wire to connect these two plates, and it will form the capacitor, right? It will have the contact potential difference. So this one will be positive charge. This one will be negative charges. So my question is, the potential difference between the aluminum and gold is CPD. And then when you use your hand to move the aluminum plate away from the gold, how the voltage will change? We are from university. This is definitely high school problems. Okay, first, are we doing some work? When we're moving the aluminum away from the gold, are we doing some work? We ignore gravity, we ignore hydrodynamic force. Are we doing some work? Definitely, because we move the electrons from the gold back to the aluminum. Definitely, yes, we are doing some work. Second, are we changing the voltage? What's the value of this voltage? It's the contact potential difference. It equals to what? It equals to the Fermi level, right? This Fermi level is a constant. So you move the boards, you are doing the work. The work is U times Q. You only change the quantity of charges on the board. You do not change the voltage because the voltage is from the contact potential. So you move away the gold from you move away the aluminum from the gold. You only change the capacitor, you change the charges, but you do not change the voltage. Okay, so that's the problem here. So once you understand this one, you don't need to worry about lift height. Because you are using 100 nanometer lift height, you are using 101 nanometer lift height, you get the same potential value. The potential value has nothing to do with the lift height. Okay, so you don't need to worry about the lift height, but we still need to play around with the lift height. So once we change lift height, what we change? We change definitely the force. The force is Z lift square, right? So if we change the lift height, we will definitely change the force. We change the force, we change the deflection, we change the deflection, we change the vertical. So we can tell from here, the low Z lift, it will give us strong signal. Strong signal means low noise. So in principle, we want our lift height to be small. But the idea of the KPFM or the idea of the EFM is we want our force to be what? To be electric field force. We don't want our force to atomic force. So we need to get out all the atomic force. If the probe is too close to the sample, the atomic force is back. So we don't want atomic force to be here. So the Z lift should not be too low. And Brucker did some experiments. I think it's on page, yeah. No, not here, not this page. Yeah, Brucker did some experiments here. So he is detecting the this is some organic materials, this is some polymer on the surface, and this is a polymer, this is substrate. They are two materials. These two materials, they should have different charges. So we use KPFM to detect the different charges. So Brooke did this experiment by reduce the lift height from larger to 28, 27, 25, 24, 23, 29, 22. And you can tell 28 and 27, we almost get the same results. The polymer part is completely black. We cannot tell the details of the polymer because the KPFM is tell the charges. It's not tell the morphology. It does not have that high resolution to tell the difference at atomic levels. So the KPFM should not get the information here. But if we reduce the lift height from 27 to 25, we can show details here. We can show the details here. And these details, it should not come from the charge. It from the morphology or it from the atomic force. So we think, and if you reduce the lift height more, you can see more clearly this kind of details here. But again, we don't think these details reflect the charge distribution. These kind of details, they are all from atomic force. So we think those things, they are artifacts. They are artifacts. We want our KPFM to be something like that. It's only the charge distribution or it's the Fermi level distribution. It should not tell us the morphology stuff. So the broker usually will use the lift height around 30 nanometers. Below 30 nanometers, it will be suspicious. But the current, some researchers, they just want to use the KPFM as a way to distinguish their stuff. They don't care if this potential value is quantitatively accurate. They just want a beautiful image. And if your purpose is to get a beautiful potential images, go ahead, you can reduce the lift height. But again, the potential value may not be accurate, but definitely it will give you the beautiful images. Okay, yeah, I understood that there are some users, there are some researchers, they like this graph. They think this one is better than this one. Okay, yeah. Okay, so we are not here to show you how to make a beautiful artifact data, but that's the current situation. If you need it to be, if you want something like this, just reduce the lift height. If you want your sample to be accurate, increase the lift height. Just increase the lift height, but don't increase the lift height to be too high. And then if your lift height is too high, your signal is gone. This deflection is too small, and it cannot get the accurate VDC. So usually we are using around 30, 40, 50, something like that. And if it's larger than 100, signal is quite weak. Okay? And then that's the same reason we will use a conductive probe, because conductive probe can give us larger electrical field force. It's the same as the EFM. In principle, you can use a semiconductor probe, which is the silicon, the silicon tip, but the signal is weak. We prefer the conductive probes. So we will coat it as the with the metal layers. Okay, so that's the KPFM. Okay, so again, the KPFM, for example, for the amplitude for the amplitude, for the AM, our signal is from the deflection, so we prefer low K. We prefer low K. And for the FM, we are detecting the delta omega 0, right? Delta omega 0 equals to the omega 0 2K dFTS over dz. So again, we also prefer low K probe. Okay, that's the KPFM. We just use some low K probes, and then the next is the Brooker's recommendations. Brooker recommendations. We have a preferred probe. The name of the probe is the peak force quantitative nanoelectric PFQNE-AM. This probe, I think we used to use this probe for KPFM measurement in MCPF. Our lab has lots of this kind of probe. The advantage of this probe is the probe is quite soft. The probe itself is quite soft, so the K is quite low for these probes. But if your probe is too soft, you cannot use that for the tapping mode. So Brooker will has some techniques called the peak force tapping, and the peak force tapping is used to get the morphologies. So for this kind of thing, either AM or FM, they are just a lift. For your morphology, you can do anything you want. You can do tapping mode, you can do contact mode, you can do peak force tapping mode. And for this kind of soft probes, they cannot do tapping mode. So if you need to use this kind of soft probes for KPFM, either AM or FM, you just choose the peak force tapping mode as your morphology, as the main scan. Okay, that's this probe. And the second thing about these probes is the probe itself, it does not have the metal coating. This probe is not coated with any palladiums or cobalt. It's just the silicon. And to increase its conductivity, this probe is heavily doped. So this probe is heavily doped. I remember it's using tin, and this probe is heavily doped, so its conductivity is much better than the normal silicon. But again, it's not as conductive as the palladiums or cobalt as metals. It still has relatively large resistance, but it is conductive enough for KPFM measurement. So if you want to use this one, it's good for the KPFM measurement, but not good for the current measurements. Okay, so because this one they don't put any coating on the tip, so the tip radius is large, so the resolution is relatively higher. So that's the advantage of this probe, but it also has disadvantage. It's not as conductive as your normal metal coated probes, so the signal is relatively lower. So it increased the resolution, but reduced the signal a little bit. And of course, it has another advantage is that there's no metal coating on the probe, so it does not worry about if the metal coating is gone, the signal will change. No, it's always it is always silicon. It's much easier. Okay, and if you okay, let me find my eraser. if you want to do some quantitative study, especially for EFM, this one may not be your good choice because it is not metal. It is heavy doped silicon. It is still a semiconductor. The Fermi level of semiconductor is different with the Fermi level of the conductor. It will make your theoretical calculation a little bit hard. So if you are doing a theoretical study, just use the metal coated probes, not this one. Okay, that's the advantage of these probes. Okay, I think that's all about our normal KPFM. Any questions about this? Okay, so it's just use the Kelvin's method. Just use Kelvin's method, adjust the VDC, we get the vertical equals to 0, or we get the frequency shift to be 0. That's the Kelvin's method. Okay? Well, it is. So the final time we will give it to a so-called high voltage method. This one, I don't think we should call it a KPFM because it's not Kelvin. So we go back to the theory here. We take a look at this theory here. So if we have a tip, we have a sample. If we apply a VDC on the tip, and we apply a VAC sine omega t on the probes. And our idea is if VDC equals to the CPD, this term will be 0, right? That's the idea of the AM. Okay, so when the people look at this term, they found one thing. So this one, the detection of this method is limited by the range of the VDC. If the surface potential, if the potential is large, the VDC should be large. That's the idea, because we need to compensate the potential difference. But the VDC in current instruments is just a negative 10 volts to 10 volts. So it can only measure relatively low voltages. This low voltages is enough because if we want to it used to be work function, it's enough. There's no work function, it's larger than 10 volts. It's okay. But if we detect a surface charge on insulator, this VDC, this surface potential, as we said, can be kilovolts, can be quite large, right? So for this kind of sample, we do not have enough VDC to compensate it. So for this kind of way, how we do it, then they take a look at these two terms. So if VDC equals to 0, we don't apply any VDC at more. So the force, the electric force, will be a DC term plus DC over dZ times surface potential. Times VAC sine omega t, and plus, this one will be a negative, plus the 1 over force dC over dZ, this is VAC square. and cosine 2 omega t. So this term is related to the surface potential and the VAC, and also the dc over dz. This term is related to dc over dz and the VAC square. If we divided this one by this one, we can get rid of the dc over dz. So the amplitude at omega divided by amplitude of 2 omega, we get 4 times surface potential over VAC. So we measure the amplitude at omega. We measure the amplitude at 2 omega. Then we divided them and we get the surface potential. We get the surface potential. Of course, this one is not the Kelvin way, because the Kelvin way, the idea of the Kelvin method is we need to compensate this one. But this one, we do not apply any compensation. We measure it directly. So in Brooke way, we call this one KPFM, high voltage, because we can measure high voltage surface potentials. But no, this one is not Kelvin. It's just Brooke's name, Brooke's nomenclature. And in the reference, you will find different names for this method. Sometimes they call it open loop potential detection. Some reference, they will call it a low compensation or long compensation potential the detection, blah, blah, blah. And if you take a look at its theory, it's just the same as this one. Okay? So of course, in your publication, you can just use any name, it's okay. You can call it KPFM high voltage, or you can call it open loop potential detection. Doesn't matter. Just let the reviewer knows you are doing this thing. Okay? So in this method, it's much easier. So we just need to apply a voltage on the we just need to apply a VAC sine omega t on the tip. And then we measure the amplitude at omega and 2 omega, and then we can get it out. And this thing does not need any special mathematics at all. So some researchers can configure this measurement out just by themselves. And in all this, when we don't have the KPFM way, we will use this kind of method. And this one, we call it KPFM high voltage. Okay, so it does not mean we compensate a high voltage, but we calculate it out from we calculate the surface potential out from this method. Okay, so that's the KPFM H way. And for you guys, you may not use this one too frequently, because when you use this one, it's not Fermi level, so it may not be related to the material properties. It's more about the charges. So that's the KPFM H way. But even you are not using this one for the surface potential detection, I still recommend you to use this one if you want to find dc over dz. If you want to study your materials dielectric properties, if you want to get the dielectric coefficient of your materials, you don't want to use the EFM way, you can use this way. Because this way, you can get this term, this amplitude at 2 omega. This term is just quite simple. It's related to the VAC, and the VAC is you applied, you can easily get it out. And then it's proportional to DC over DC. As we said in the morning, DC over DC is just a dielectric coefficient, right? So if you want to study, or if you want to distinguish materials with different dielectric coefficient, you can use this KPFM HV method in Bruker's machine, but you don't look at the potential, but look at this term. Look at this term. This term can give you the DC over DC. It's also useful. Okay. Okay. I think that's all. That's all the topic about the KPFM in the afternoon. It's not that I think it's easier than the EFM, but it's more useful because it gives us some values, and this values is related to the properties. It's not like the EFM because EFM give you the phase or frequency, and the phase frequency is too far away from the properties. So the KPFM is used much more frequently in our researches, and we just need to be careful that we are measuring potential, not always the Fermi level. Okay, I think that's all today. Thank you.